The first file is plates. The first sequence in the file is New Zealand's volcanic zone. New Zealand's North Island is one of the most closely studied volcanic landscapes in the world. We probably know more about this volcanic zone than any other. There's not much of this region's physical geography that hasn't been investigated, measured and analysed. But we weren't always so well informed. Not that far back in time, it was a different story.
Until about 150 years ago, geologists still didn't have much of an idea how a volcano works. They called them burning mountains and thought that their heat came from coal and oil just beneath the ground.
The Maoris, though, the people who lived here in New Zealand before the Europeans arrived, were much closer to the truth. One of their legends said that a god burrowed at great speed through the ocean bed and broke through with terrific force onto the surface of the land. Since then, there have been any number of theories that try to get to grips with the major forces at work near the Earth's surface, the forces that have laid the foundations of our physical landscape.
The latest is the theory of plate tectonics.
From its middle to its edge, the Earth measures 6,400 kilometers. From the core all the way out to very close to the surface, temperatures are incredibly high, between 1,800 and 3,100 degrees centigrade. At this sort of heat, the rocks are mostly liquid. The outer skin, about 30 kilometers thick, is known as the crust, and this is what we live on. The plate tectonics theory, though, tells us to tear up the map of the world as we know it and start all over again. Forget the continents and oceans. What really counts is the division of the crust into 7 huge pieces that the theory calls plates. These plates behave like rafts on water. They are solid objects floating on the almost liquid rocks beneath. And just like rafts, they are on the move, ever so slowly, but they are definitely mobile. The next part of the theory picks up on that mobility. It says that some of the major features of the Earth's crust are related to the way the plates move in relation to one another. The theory identifies 4 main plate movements. The first is known as subduction. This is when one plate is disappearing beneath another. The second is called compression. This is when 2 plates are colliding head-on. It's also, for obvious reasons, one of the ways in which mountain ranges are formed. Next is extension, the complete opposite, when 2 plates are moving apart. This movement leads to the formation of huge ridges and depressions. The fourth is known as a transform boundary, 2 plates sliding past one another horizontally.
Like lots of processes happening in the physical landscape, these plate movements take place over extremely long periods of geological time. So much so that we are completely unaware of them. Occasionally though, and it's always on the plate boundaries, something happens very quickly.
The friction between the plates generates such high levels of heat that the rocks melt and shatter. There is now a route open to the surface through the crust from the molten rocks beneath. The scene is set for one of the most dramatic events in nature. White Island is, for now, the most active volcano in New Zealand. It's just the tip that shows above the ocean. Its base on the sea floor is 18 kilometers across. White Island, strange name for a black inferno. The land in the heart of the crater is totally alive. It's breathing, puffing and snorting. There are sudden flashes of colour from the raw chemicals that have been spewed up from deep inside the Earth. Yellow for sulphur, white for silica, a slimy blue for some other kind of subterranean soup. In the middle of it all, a lake, the result of the usual heavy New Zealand rainfall collecting in the crater. There's a definite pattern as to where these extraordinary volcanic landscapes occur. You can't have them unless there's a plate boundary in the neighbourhood. It's not a good idea to hang around for very long.
At somewhere around 90 kilometres beneath me is one of the most active plate boundaries in the world. The Pacific Plate is being dragged beneath the Indian-Australian Plate, and the molten rock that's produced by the heat of this gigantic movement is surging up and feeding the White Island volcano. Just a month ago, a huge plume of ash, 1,500 metres high, shot out of the White Island volcanic crater. Since then, the ground has been shaken by thousands of tremors. If you live in a country that has plate boundaries beneath it, then you live on a very twitchy piece of the Earth's crust. Well, the next load of ash is on its way, so I'm off.
20,000 square kilometres of the land on New Zealand's North Island is made up of rock that has been poured out from volcanoes. In 232 AD, the most powerful eruption in historic times happened here in the volcanic region of Lake Taupo. The eruption cloud rose 50 kilometres above the lake. The noise could be heard 4,000 kilometres away. Records discovered in China and the Roman Empire tell of 20 years of blood-red sunrises and sunsets. In 1886, plate movements opened up this 17-kilometre-long gash at a place called Tarawera. There aren't many places in the world where physical geography is quite as fresh in the landscape as here. It's not difficult to imagine the drama that happened. It was a 17-kilometre-long line of fire. It lasted about 5 hours. When it's beneath the ground, molten rock is known as magma. On the surface, it becomes lava. And Tarawera's lava spread out to over 100 kilometres away. Eruptions can be so frequent that plants have no time to grow on the new land before the next eruption happens and another layer of molten rock is spread over the ground and solidifies. The layers, one for each eruption, are often of different colours and stand out loud and clear in the landscape. In the areas close to the main volcanoes, the layers can be up to 500 metres thick. Dating the layers, and therefore working out the date of the eruption, is no problem.
And that is down to the fact that the heat of the eruption is so intense that trees get incinerated in its path. Geologists can take a sample of the burnt wood back to the lab, and with a testing system called carbon-14, can put a date to when the tree met its end.
New Zealand geologists have become experts in the forces behind volcanic landscapes. A lot, though, still remains unpredictable. But nowadays much more is known about what is dangerous and irregular and what is relatively safe and reliable, like the weird repetitive activity in the geothermal areas where gas and liquids constantly bubble up from underground. On occasions, though, no amount of expertise can cope with the totally unexpected. For some events in this restless volcanic landscape, there can be no warning, like one that happened at the end of 1954.
It was 8 o'clock in the evening on Christmas Eve, still broad daylight in the middle of summer. And Mount Ruapehu, the largest of the volcanoes in the volcanic zone, looked quiet enough.
Then, with no warning, the ground at the summit, close to the crater lake, gave a big twitch. Nothing unusual about that in this part of the world, except that it was the wrong kind of twitch, the sort of twitch that kicks off a lahar.
Lahar is an Indonesian word. Indonesia, like New Zealand, being on a plate margin and home to numerous volcanoes.
The twitch cracked the wall of the crater lake. 35,000 cubic meters of water were ready to leave.
And when that happened, a highly mobile gunge of ash, rocks, boulders and water started to surge downhill. Those people who've seen a lahar often describe it like watching a river of wet concrete on the move. At this spot, the lahar from Mount Ruapehu was doing 60 kilometers an hour, loaded with volcanic ash, tree trunks, and very likely most of these boulders. It was heading straight for a railway bridge just around the corner.
The bridge was no match for the lahar. It was swept away in a matter of seconds just before a train arrived. 151 people were killed. Since it was first put forward, the theory of plate tectonics has always said that volcanic activity isn't the only product of plate movements. There's another major drama in the Earth's crust which has a very direct effect on people, like here in the town of Franz Josef, which sits right on top of a plate boundary.
It's a transform boundary, with the Pacific plate on this side of the road moving that way, and the Indian-Australian the other. There are no volcanoes in the area, but the plate movement here can often result in another kind of dramatic natural event.
In the early morning of January the 17th, 1995, instruments in a lab in Western Japan picked up a burst of intense electromagnetic radiation. It was the signature of a massive earthquake which had just struck the city of Kobe from its epicenter 20 kilometers to the southwest. There was no warning. 180,000 buildings were destroyed. An urban area 20 kilometers long and 4 kilometers wide was totally wrecked. Nothing moved in or out of Kobe by road or by rail for 3 days. The root of the disaster was a shock that happened on the boundary between the Eurasian and the Philippine plate, a boundary that runs right beneath the city. There is a direct relationship between plate margins and earthquakes throughout the world. Japan is very vulnerable to earthquakes because of the country's special physical geography. Everything is packed tightly into the precious stretches of lowland, which make up only 20% of the land area. Japanese cities are one of the most complex urban landscapes on Earth, mixed up, multi-layered, fragile. When it comes to earthquakes, another problem for Japan is that huge areas of land have been reclaimed from the sea. Kobe itself has advanced 15 kilometers seaward in the last 20 years. The trouble is, the reclaimed land, which now accounts for a third of all Japan's coastline, is relatively soft and wet and allows the shock waves from earthquakes to carry on for long periods of time. During the Kobe earthquake, at locations on solid rock, the shaking lasted 20 seconds. On the reclaimed land, it went on for 2 or even 3 minutes. As its human landscape becomes more and more complex, Japan becomes more and more vulnerable to earthquakes. The country has spent a fortune studying them, but until now, no way of predicting when they will occur has been discovered. It did happen here in the UK, tens and also hundreds of millions of years ago. On many occasions, active plate boundaries developed beneath this part of the Earth, with the usual consequences. Today, the remains of those dramatic events are still with us. Especially in the north and west of the UK, the igneous rocks that force their way up from deep underground are part of the landscape. Igneous rocks are usually very tough. This one, in a quarry in Aberdeenshire, is one of the toughest of the lot. It takes a powerful thump to break it up. It's granite, one of the commonest rocks in the world, and it was formed during a volcanic period as a thing called a batholith. The origin of the batholiths in Aberdeenshire dates back to 500 million years ago, when magma built up towards the surface of the Earth, pushing its way through other rocks in its path and growing into the shape of a dome. Before reaching the ground, the magma cooled down very slowly, turning into a solid mass of granite, a batholith. Over millions of years, erosion wore down the softer layers of rock above it, uncovering the top of the batholith. Put back the present day, and that's why there are hills of granite in the Aberdeenshire countryside.
The Aberdeen granite companies really began to get busy digging into their batholiths about 150 years ago. It wasn't until then that machines had been invented powerful enough to dig out these huge boulders and shift them around. Massive holes like this one began to appear in the Aberdeenshire countryside. For the people of that time, the Victorians, there's no doubt that granite was one of their favourite rocks. They were very fond of it for its colours, and granite has several of them. The 3 main ones are sort of pinkish red, a mottled grey, and one that's almost black. They also liked it because it's one of the toughest building stones around. And if there's one thing the Victorians liked to do, it was build.
Granite got into everything: bridges, lighthouses, quaysides, curbstones, and all sorts of buildings. The city of Aberdeen was pretty well made from it. Granite's resistant to pollution, mildew, bird droppings, and frost. It doesn't deteriorate in bright sunlight. It always looks new, and it's still in great demand.
It's one of the best road surface materials we have. Just a thin layer of these chippings mixed with tar and spread on the surface of the road will withstand any amount of pounding from heavy traffic. It's still a pretty useful igneous rock, 500 million years after it first rose up from inside the Earth.
This is probably the most public lump of igneous rock in Britain, just across from Edinburgh's main shopping street. On top, there's Edinburgh Castle.
What this is, slap bang in the middle of the capital city of Scotland, is the nearest thing in Britain we've got to an actual volcano. It erupted a very long time ago. More to the point, unfortunately for the inhabitants of Edinburgh, it's never likely to do so again.
The name for this pile of igneous rock is a plug, and this is how it came about. Peel off the present day and go back 350 million years. Once upon a time, there was a volcano here. A cross-section through it shows its internal structure. Round the edges, layers of volcanic ash and lava. Through the middle, a huge pipe of magma, molten rock. The rock cools down and goes solid, really solid, blocking up the volcano. And this is the origin of the word plug. Next, the sea level rises. We're rushing through quite a few million years here, during which time new layers of rock build up on the seabed. The sea level drops, all dry land again. Now comes an important sequence of events. Through more millions of years, the land surface is eroded away, but because the plug is very much harder than the other rocks around it, it stays sticking up above the surrounding land. Put back the land surface. And there's the spot for Edinburgh Castle. The plug rises 70 metres above the surrounding land, making the castle an easy place to defend. For hundreds of years, it was a Scottish fortress. Up here, the Scots had a bird's-eye view of enemy armies marching up from England.
And thanks to this commanding position, give or take a couple of times when the invaders got in, the Scots managed to send the English packing.
In Northumberland, there's an igneous rock that's become rather famous because of a Roman emperor called Hadrian. He was on a visit to this stretch of his overseas possessions in 120 AD.
Apart from doing a tour of inspection of his troops, he'd come here for a special purpose. He'd decided that this remote part of his empire should be properly fortified. What he had in mind was a wall built right across the country, a proper frontier that said, "Keep out, this is the Roman Empire." Well, just over there, he found the ideal spot for it.
All of a sudden, the ground fell steeply away, and he found himself on a sort of cliff. What's more, the cliff carried on to the east and west, just the right line-up for his wall. The cliffs were a real bonus. A wall on top would give the Roman army a high viewpoint. What the Emperor Hadrian didn't know was that what he had his eye on was no ordinary cliff at all, but a special kind of igneous rock called a sill. It was formed 295 million years ago. A thin band of magma forced its way upwards from a plate boundary, a bit like a filling in a sandwich. It stopped short of the ground surface, cooled and solidified into a hard, resistant mass. Millions of years of erosion wore away the rocks above it until the sill was exposed on the ground surface. Typical of an igneous rock, it's much harder than the rocks next to it, so it ends up much higher than the surrounding land. Put back the rest of the present-day landscape and you can see how the sill has become a long line of cliffs overlooking the Northumberland countryside, the cliffs along which Hadrian was to build his wall. The wall was built from rocks quarried from the sill itself. Thanks to its hardness, there are still long stretches of it left after 1,800 years. What survives today is the remains of a curtain of stone once 100 kilometres long, drawn across England.